Hello everyone, welcome to Module 8, where we're going to be dealing with rotational motion. Now rotational and angular are actually interchangeable words. So sometimes you'll see the word rotational, sometimes you'll see the word angular. It all deals with the same thing, and you can interchange those words. So, in rotational motion, what we're going to do is we're going to take what we did in the first 7 chapters of the book in linear motion and apply those same laws of physics to rotational motion. Linear is moving in a straight line, whatever straight line distance you cover over whatever unit of time, as where rotational is dealing with objects spinning. Now, in linear rotational, that's L and R here, not left and right. In linear motion, we had 5 major ideas we've been discussing: distance, velocity, acceleration, force, and mass. And we use those to get other quantities and so forth. They all have rotational equivalencies. The rotational equivalency of distance is an angle, which we use Greek letter theta to represent. But theta represents an unknown angle. An angle is simply rotation. If I'm facing this direction and I rotate to face that direction, I've created an angle. Or if you think about it, there's something spinning, it's the amount of revolutions or rotations that it makes. A tire spinning in a car revolves around the axis. The linear quantity was velocity. Its rotational equivalent is rotational velocity, which we use a lowercase omega to represent. Looks like a W, but it's lowercase omega. And that's how fast something is spinning. We have your basic linear acceleration, is how fast or slowly that velocity increases or decreases over time. Same thing for rotational acceleration. We use lowercase alpha, and that represents how fast the spin increases or decreases in speed. Force has a rotational equivalent of torque, which I'll be talking about more specifically in the next video. And mass has a rotational equivalency of rotational inertia, which again I'll address in the 3rd or 4th video here. Now, these have their individual formulas, which I'll talk about momentarily. But the rest of these, all the formulas that you had for distance, velocity, and acceleration have rotational equivalents. It's the same mathematical relationship, but we just use different symbols to represent linear as opposed to rotational motion. For instance, the 2 velocity formulas we've been dealing with, just distance over time, if it's traveling with a constant velocity, or final velocity is initial velocity plus acceleration times time, if it accelerates. Same thing in rotational motion. Rotational velocity is the angle over time, or final rotational velocity is initial rotational velocity plus the rotational acceleration times time. Notice mathematically they're identical. It's just different terms, I should say, or different symbols to represent the linear as opposed to the rotational motion. Same thing with your basic acceleration formula, final minus initial velocity over time. So rotational acceleration is final minus initial rotational velocity over time. Your 3 different distance formulas, and all the conditions that went with these 3. D equals Vt, no acceleration. 1/2 at squared, acceleration starting from rest. V sub ot plus 1/2 at squared, that is acceleration not starting from rest. And the 3 rotational equivalents also use the same exact conditions. Theta equals omega t, that's if the object is spinning with a constant velocity, constant rotational velocity. Theta equals 1/2 alpha t squared, that's if it's accelerating starting from rest. Omega sub t plus 1/2 alpha t squared, if it's spinning and accelerating and not starting from rest. And then we have Newton's second law, force equals mass times acceleration. Torque equals your rotational inertia, I times alpha, your rotational acceleration. And the m1v1 equals m2v2, the conservation of momentum. We have what's called the conservation of angular momentum, which is I1 omega 1 equals I2 omega 2. Now those are all the linear formulas with their equivalents. We have 2 formulas for concepts in rotational motion that have linear formulas. The first one is torque. Torque is simply force in rotational motion. That's going to be force times what we call the lever arm. That's what the L stands for. And that is something I'll explain here in the 2nd video. And the second one, rotational inertia, which is the rotational equivalent of mass, is equal to mass times the radius squared. So it's not just the mass we're considering, it's where the mass is placed on the spin of axis of rotation. So everything that we did with linear motion, we're going to have the same types of problems, examples, and so forth, just dealing now with rotational motion. And in the next video, we're going to look at specifically torque.